communicated in a way that makes sense to people. Called probability of superiority, which in this example is a little bit of an awkward term, but it just means that if we draw a random pair of people, I think of this as the junior high school dance problem. If we choose a random boy and a random girl, what's the probability that the boy is taller than the girl? There are a couple of ways to compute this in Python world. So one way to do this is by lining people up and just pairing them up and computing the fraction of pairs where the female is taller than the male. And you can do that using zip. So if you are more comfortable with Python stuff and you like zip, then you can zip together the male and the female samples, and that's going to pair them up one by one. And for each pair, it'll count the number of times that X is greater than Y. Turns out to be about 91%. So in the US adult population, if you randomly choose a man and a woman, the man will be taller about 91% of the time. And then if you want to get all NumPy with it, you can do the same thing using the logical arrays that I mentioned. Questions? How many people have you... tell me whether you have got to the end of the notebook or whether you would like a minute to read about Cohen's effect size before I go on. Got to the end? Would like a minute to read about Cohen? Okay, we will take a minute to finish up the notebook, and then I will debrief. Okay, two things I wanted you to see here. One of them is Cohen's effect size, which is a way of quantifying the difference in means between two groups. It's taking the means and standardizing them by dividing through by standard deviations. So it's a way of saying the difference between these two groups is some number of standard deviations. The slightly tricky thing is that it's not clear which standard deviation to use, whether it's one group or the other. And you wouldn't want to compute the standard deviation for the whole population put together, because if it really is two groups with different means, then the global standard deviation would be quite big compared to the standard deviation within the groups. So that's why the denominator there is the pool standard deviation, which is basically a weighted sum of the two, or weighted mean of the two standard deviations. So the details of that are not super important, except that the denominator is meant to be a measure of the variability within the groups. And this is saying that the difference in means is a certain number of standard deviations. The nice thing about that is that the mean is in units of centimeters in this case. The standard deviation is in units of centimeters. Those two things will always be in the same units, so when you divide them, that ratio, centimeters cross out, and the result is dimensionless. So Cohen's effect size, one of the things that it's useful for, is making a comparison between different studies. So if I tell you that this study found Cohen's effect size of 2, and that one found the Cohen's effect size of 1, you can compare those two studies without knowing anything about the domain, without knowing anything about the units that they were measured in. Those things mean the same thing, no matter what. The other reason it's useful is that if I give you Cohen's effect size, you can compute those other two things that I mentioned, the misclassification rate and the probability of superiority. So it's one number that's comparable across different studies, and if I give it to you, you can compute the other kind of important practical things that matter. There's only one drawback to Cohen's effect size, which is that most people don't really know what it is. If you're in a field where it's widely used, you're familiar with it. If not, it takes a little while to get calibrated. So if I tell you that it's 2, for example, that might not mean anything to you until you look at a picture like this. So that's what it looks like when there's a difference in means of 2 standard deviations. And you can see from that overlap area, you can get a visual representation of the misclassification rate. And if you get interactions working for you in your notebook, which is not a given, But this is the other kind of cool tool that I wanted to show you. If you have not used Jupyter before and you have not seen this, you might like having this slider where you can adjust Cohen's effect size. So when it's 2, that's what it looks like. And let's see, when it's like 3, interesting. I'm having the same problem that someone else had, which is, so the way that this is supposed to work is that it updates that figure. But what's happening for me and what might be happening for other people is that instead it's making lots and lots of figures. That's too bad. Well, tell you what, instead of interacting, you might find that it's easier to just use this previous cell number 26, and just plug in different values here. So let's do that. So with Cohen's effect size of 1, that's what it looks like. So that's not a super strong effect. There's a lot of overlap. So the misclassification rate here is half of that overlap. The overlap there is the area, and half of that is misclassification. The probability of superiority is now down to 74%. If you are into psychology, differences between men and women in psychology tend to be like 0.5 or less, and that's what that looks like. So when you see newspaper headlines that talk about all these differences between men and women in various cognitive ways, try to find the effect size, and if it's 0.5 or less, you probably don't care. On the other hand, if you see something like 3, you should be somewhat impressed. So 3 tells you that basically if you tell me your score on this scale, I can classify you with pretty high accuracy. So 3s, 4s, 5s, meaningful, 0.5 and below, maybe not in practical terms. That's a great question. So let's say I tell you it's 2. Yeah, so I'm telling you effect size, and I tell you, okay, I estimated that Cohen's effect size is 2. Your natural question is, well, how precise is that estimate? How much might you be off by? And we're going to answer that in the next notebook. Yes, sir. Yes. Yes, so I'm treating everything here as normally distributed. Most of what I'm doing, you could replace the distributions with empirical distributions. So just draw random values from an actual sample rather than from a continuous or analytic distribution, and the whole process would be the same. And in fact, we're going to do some of that in the 3rd notebook. Other questions? Yes, sir. Yes, good question. So I think you're talking about this cell here, where I'm computing Cohen effect size. Since I have a laser pointer, I have to use it. So right here, I'm computing a Gould variance, and then a square root. And you're asking, why did I compute the variance and then square root it? It's because I wanted to take the weighted sum of the variances. And I have to do that in variance land. Yes, I might have done some unpacking when I translated this. So here, if you look at the math, I've got S1 squared and S2 squared. Yep, those are the variances. Beautiful. I put it in the 5-point font. Let's see, all right, crank that up. There we go, how's that? There. Okay, so to summarize what we've got so far, we have a bunch of different ways to quantify a difference in means. Many of them are useful because they are comparable across different studies. So if I tell you probability of superiority, that is expressed in practical terms, and it is comparable across studies. Cohen's effect size also has this nice property and is commonly used in a lot of fields. So that was part one, which is telling me about effect sizes that are like differences in means. Part two, we're going to talk about differences in proportions, and I'm going to use some real data that came out a few years ago. This is a study of peanut allergies in young people. And in particular, it was children, I think they were about 5 years old, who had tested for a certain inclination toward allergies. So it was a little bit of a unique subpopulation. And they actually did a randomized controlled study where some of them were told to avoid peanuts, and some of them were told, yes, you should go ahead and eat peanuts. And then they checked to see who was more likely to have a peanut allergy some number of years later. I think it was a few years. And it turned out to be a pretty substantial difference. If you avoided peanuts when you were like 5 years old, the chances that you would develop a peanut allergy was about 17% for this particular group again. If you went ahead and ate peanuts, you had only a 3% chance of developing allergies. So this is the actual text that was in the report, and it's giving you all these numbers. So they were randomized. I forget some of the details of the study, but you can look at it more. But here's my question for you, which is if you had to summarize that result with a single number to tell me how big that effect was so that I could compare it. Let's say I want, there are other treatments or other allergies I might be interested in. I want to make comparisons between studies in a meaningful way. What's the single number that I could use to communicate the magnitude of that effect? I would like you to chat with your neighbor for a couple of minutes, think about it, and then I'll ask for suggestions. All right, let me hear some suggestions. How am I going to communicate the magnitude of this effect? And think about this like you're talking to a parent who's trying to decide whether to give peanuts to their children. What would you tell them? Come on, somebody be brave. Yes, sir. 5 times more likely. Okay, that's one way to do it. Other possibilities. 14% as the effect, percentage points. Yep, so that in some you're just taking the difference between two percentages in percentage points. Yep, so one of those is like a absolute difference in percentage points. That's, I think, a relative probability or ratio of probabilities. Yep, oh good, yes? Who am I representing here? Yeah. Who's it? Cui bono? Who benefits? Yes. Who funded the study, right? Okay, so one possibility is the 14 percentage points. One of the challenges is that you have to figure out which one is the control group and which one is the treatment group. And in this experiment, it's not clear whether withholding peanuts is a treatment or whether administering peanuts is a treatment, and so you could express it in either direction. Minus 14. One difficulty, if you express things in terms of percentage points are not a good way to compare different studies, because if I tell you that something went from 3% to 17, that might be a really big deal. But if you're like right in the middle of the percentage range from 43 to 57, that might not actually be such a big deal. But if I take some infinitesimally small risk like 0.01 and I turn it into 14.01 or whatever, I've done you some serious harm. So percentage points are a problem if you are comparing things that are at different range of probability. The other possibilities, you could talk about the percentage decrease. So you could say you will cut your probability of getting allergies by 83% by going from 17 to 4, or 17 to 3. The only problem with that is that now that asymmetry problem becomes much worse. So now going from 17 to 3 is a reduction of 83%. Going from 3 to 17 is an increase of 467%. So that's kind of awkward. The other thing that's kind of bad is that people get confused when you start talking about percentage differences in percentages. You will lose your audience. So those are a couple of challenges there. In medicine, the odds ratio is very popular, and this we now have to take our probabilities and express them in terms of odds, and then take a ratio of two pairs of odds. If you are not familiar with odds, it is just another way of expressing a probability. It is equivalent in the sense that if I give you probability, you can compute odds using that formula. If I give you odds, you can compute probability. So it's equivalent in that sense. So here I've got probabilities 0.03 and 0.17. I can convert them to odds, being those values that you see there. And then the odds ratio is 0.151. Which may not mean a lot to you, but sort of like Cohen's effect size, people who work with odds ratios learn to get calibrated. They have a sense of what that means. And so now you could express this either way. Again, we've got the problem with which direction to go in. I could either say that if you eat the peanuts, you decrease your allergy rate, and the odds ratio is 0.15. Put it the other way around, avoiding peanuts will increase the allergy rate with an odds ratio of 6.6. That's how you're going to see it in medicine most of the time. I'm going to suggest one other possibility, which is the log odds ratio. So take those same numbers that we just had a minute ago, and it's a ratio. If you take the log of a ratio, that's going to be the difference between the logs. And one nice thing about it is that it is symmetric. The log odds ratio is 0.82 in this case. Either way, and it's just the sign that changes depending on which direction you work in. Now, if I had my magic wand and I could make everybody in the world use log odds ratios, I would. Log odds ratios have a lot of really nice properties. When you are talking about probabilities, they work across the entire range of probabilities. It doesn't matter whether it's tiny, medium, high probabilities. It's the same information content. And actually, if you want to get into information theory, the log odds ratio is a measure of the information content. If you tell me what the treatment was, that'll tell me how I'm going to do a Bayesian update about how much I should believe you're going to get a peanut allergy. And they add up. If you apply several different treatments that have log odds ratios of 1, 2, and 3, the total of all of those treatments is 6. At least if I assume that they're independent. Yes? Shoot. The problem with log odds ratios is that nobody knows what they are cute, but nobody knows what they are. You have two axolotls. How many other people knew what an axolotl was? All right, they're not quite as obscure. How many people knew about log odds ratios? They're exactly the same. So my analogy is apt. They are, and they're very cute. Although I always get them confused with an adolescent, which I guess is not good. That's the spear throwing thing. Oh, interesting. Interesting. This is great. We might be off topic, but this is really good. I have only myself to blame. To summarize, there are a lot of different ways to express this. None of them are perfect. There's a little bit of a trade-off here from left to right. The things on the left are problematic from a mathematical point of view, but people understand them. The things on the right are in some sense elegant and mathematical and all that, but for a popular audience, you're not going to get people to understand that. And that's the trade-off that I'm suggesting, is to express effect size. There's probably not one ideal way to do it. You want to choose something that is meaningful in context. You want to choose something that makes sense to your audience, but there's a conflict there. You see? I suggest we take a break. Let's resume in 10 minutes, which will be 2:40. If you have questions for me, I'm happy to talk during the break. Hey, we should reconvene. if everyone's back from the break. I got one question, actually several people during the break were asking about this odds ratio and log odds ratio. I was singing their praises about how wonderful they are mathematically, and people were asking, how do I make sense of them? What is my intuition for those things? I will point out, I won't get into this in any depth, but the log odds ratio is the Bayes factor. So if you are familiar with Bayesian statistics, or a Bayesian update using Bayes' rule, the Bayes factor is a measure of the information content. And if you look up the Wikipedia page for Bayes factor, it actually has a table here that was suggested by Jeffries. Now, you don't have to take this as gospel, but it's a general notion of a mapping from a log odds ratio to how strong that effect is. This particular mapping is going to depend on the domain, so I wouldn't take it too seriously, but it's at least a step toward getting calibrated. But that's enough of that for now. Onward to part 2. Okay, so we are going to start talking about quantifying precision. This is the question I got a minute ago. I've measured effect size, and I'm going to tell you that the Cohen effect size is 2, or I'm going to tell you that the log odds ratio is 0.8, and you want to know, how good is my estimate? How much might I be off by? And that is a perfectly good question to ask. So let me start with a different problem, which is that suppose you want to know how heavy people in the United States are, and you decide to do a telephone survey. So you choose random numbers from the phone book, you dial the numbers at random, and whoever answers the phone, you ask them, how much do you weigh? And you write it down, and now we want to try to say something about the US population as a whole based on that way of doing sampling. And my question for all of you is, what could go wrong with that methodology? So talk with a neighbor for a minute and see if you can enumerate all the things that could possibly go wrong. I don't want to interrupt your fun, but I'm going to interrupt your fun. All right, talk to me. What are some things that might be wrong with my methodology? Why is my answer going to be wrong? I hear liars. So people might not tell me the truth. Okay, that's one possibility. Yep. So people who are answering the phone in the middle of the day might not be representative. In what can you think of, like, some ways that they might be different? So the numbers are random. I don't necessarily know whether they're at work or at home. Okay. Yep. Because some people might be in the phone book or not, and that might tell you something about them, whether they're in the phone book or not. Yep. Do they still make phone books? Good. Anything else? They might not be adults. Yes, so this is good because you're all telling me two things that are important. One of them is that the people that I get might not be representative, and you're telling me why that might change the answers that I get. Because sometimes you can have a non-representative sample, but it's still okay as long as there's no relationship between the ways that you are unrepresentative and the thing you're trying to measure. Yeah. So people might not be very accurate, maybe because they're lying or maybe just because they don't know exactly. Yep. Yes. Scale might not be calibrated. And it might be related to income, and many of the factors that we listed are related to income. And this is kind of one of the informal rules of social science, is that everything is correlated with income. Person might lie. Yep. Yep. Okay. So let me see. I put some ideas in the slides. So one of them, many of you mentioned examples of sampling bias where the sample is not representative. What that means, if the sample is representative, then every person in the population, in this case it's US adults, should have an equal probability of being in the sample. If they have different probabilities depending on what groups they belong to, then that's not a representative sample anymore. And if the thing that you're trying to measure is correlated with that group membership, then the results that you get will be biased. So that's sampling bias. But remember that there are two parts of that. There's a right level of skepticism. No skepticism is bad. Going crazy with skepticism is bad. It's almost impossible to get perfectly representative sampling. It's okay to be approximately representative as long as there's no relationship between group membership and the thing you're trying to measure. Sampling bias, some more examples. People mentioned that people who answer the phone in the middle of the day might be more likely to be unemployed. A whole lot of things that are probably related to income. So you guys mentioned several examples of that. You also mentioned examples of measurement error. Uncalibrated scale. Your question is ambiguous about whether you're asking for their weight clothed or unclothed. They might not remember their weight. They might misreport. The value neutral way to talk about lying is that they misreport. You might write it down wrong. Or one of the things that I run into in survey data all the time when I grab survey data is things get miscoded. So I did a study looking at, actually the height data that we looked at came from a very large study, 300,000 respondents. One of the problems with large sample sizes is that gives you more chances to make a mistake. They had a surprising number of people in that data set who were between 60 and 62 centimeters tall. I think there's only one person in the room right now who might have stepped out who is 60 centimeters. What do you think went wrong? Why were there so many? They were talking feet and inches. I bet there are a lot of people who are 6 feet 0, 6 feet 1. Not so many people, not so many adults. Oh, it could have been 62 inches, which is 5'2". Good point. Yep. The other thing that you see a lot is that missing data will sometimes be encoded as 99 or 999. So I did one study where I looked at birth weights for babies, and the mean came out to about 13 pounds. That can't be right. It's because I had accidentally included a whole bunch of 98 and 99-pound babies, which were respectively don't know and weren't asked or something like that. So measurement error, lots of examples of that. Third thing, so we talked about sampling bias, that's number 1. Measurement error, that's number 2. Number 3, random error, which is just the fact that you collected a sample rather than the whole population. And so if you only call 3 people, then it's pretty clear that you might, just by chance, get 3 heavy people or 3 light people. And your estimate might be off just because of random sampling from the population. So those are the 3 big sources of error: sampling bias, measurement error, and random error. Usually, sampling bias is hard to quantify, often because if you knew what was happening, you would fix it. So you might not know it, and even if you know it, you might not be able to measure it. Measurement error is sometimes quantifiable. There are some ways to do that. For example, if you have 2 different processes, and one of them is more accurate than the other, you can use the difference between them to estimate how imprecise the 2 estimates are to measure. Can be quantified. Third one, random error, turns out to be the easiest one by far to quantify, and therefore it is the one that we spend statistics focusing on and completely ignoring the first 2. Despite the fact that in practice, it is almost always the case that those first 2 are much more important than the third one. But the third one is easy, so we do it. That is my warning about everything that I'm about to tell you. I'm not the only one. Edward Tufte agrees with me and managed to express it in 140 characters. Random error is but one of 20 threats to learning from data. It gets disproportionate attention because it is the only threat that can be mathematically modeled. So, let's mathematically model it. Let's get back into the notebooks. If you will open up sampling.py, read through it, run the code, work on the first exercise, and stop when you get to stop here. Okay, we have a fix for the problem that we were having with the interaction. If you find this function called plot sample stats, search for that function, plot sample stats, and add this line at the end, pyplot.show. If you make the show explicit, that should allow you to do the interaction. And now, if you move the slider back and forth, it will update in place. So if you had that problem with interaction, give that a try. Hopefully that solves it. This is in the function that is called plot sample stats. Add this line. I want to go over a couple of things in the notebook. One of them is the distribution of weights for adults in the US is approximately a log normal distribution, which is kind of a funny shape. We're used to things like physical measurements on people and animals. Many things have a Gaussian distribution, which is this nice symmetric bell curve. The log normal distribution is not symmetric. It looks like this. It has a long tail on it. So there's sort of a central tendency around 60, 65 kilograms, but then there are heavy people who are up into the 120, 160 kilogram range. Turns out there's a reason for this distribution. At birth, the distribution is pretty close to Gaussian. And then as we become adults, it becomes log normal. If you are curious, I have a footnote in my book which explains why this is true, but it's outside the scope of our current activity. So I'm going to assume temporarily that we know what this distribution is, and I'm going to come back later and undo that assumption. But for now, assuming that we know what the distribution is, we can run simulated experiments that says, what if I took a sample of 100 people and I computed their average weight? And then I took another sample of 100 people and computed their average weight. And I did that experiment over and over. How much would the results differ from one experiment to the next? So that's how we're going to quantify the precision of the estimate, which is by pretending that we did the experiment many times and seeing how different it is from one experiment to the next. Now, the thing about this example that is going to become confusing in a couple of minutes is the difference between n and iters. So n is the sample size, and that's really important. That's the number of people that I'm going to go out and measure. And what we're going to see very soon is that as the sample size gets big, my precision gets better and better. When my sample size is small, no surprise, my precision is not so good. So n is the thing that really matters. Now, to estimate how precise my estimates are, I'm going to run lots and lots of simulated experiments. And I'm calling iters is the number of times I run the experiment. That doesn't matter very much. It just needs to be reasonably big. As long as iters is big enough, I'm going to get a good description of my uncertainty. So iters, I arbitrarily choose 1,000 just because computationally it doesn't take very long, and it's big enough that I'm going to get answers that are close enough. Okay. So n is important, that's the sample size. Iters is just the number of simulated experiments that I'm going to do. So there's just taking one sample and computing one sample statistic, and now here, compute sample statistic is the function that runs lots of iterations. And I'm using a Python list comprehension there just as a syntactic way of kind of like a faster for loop. Okay. Now,